So here we are today. This will be the third and final session, and it will be presented by Michael Angelidis. Michael will speak about the effect of earthquakes on the new chimney design based on experience that was gathered a number of years ago in one very big earthquake. I won't say yet too many details. It's important to note that Michael is one of the most prominent designers of civil industrial structures worldwide, I think we can definitely say. Michael has been president of the International Society for Civil Industrial Constructions, the CICINT organization. So without any further ado, Michael, I would like to turn it over to you. If you could please take over the screen and start your presentation.
Thank you, Albert. Hello, everyone. We'll be talking earthquakes today. The subject, as Albert mentioned, is the performance of the new chimney design in earthquakes, in particular at the 2010 Chilean large earthquakes. A few things about earthquakes. You probably know that earthquakes are generated from the movement of tectonic plates, which push their boundaries, their faults, their seams, so as to say, and the rupture of these faults here create earthquakes. Obviously, the highest magnitude earthquakes are generated near or at the fault locations. From our point of view, given the size of the Eurasian plate and the Antarctic Atlantic plates at the bottom, this part here is the highest stressed area. This fault line is sometimes called the Ring of Fire. It's the west coast of the Americas, from Alaska down Japan, Philippines, Indonesia, and through New Zealand. And then there's another large fault line that extends past northern India, the Himalayas, and on the other side, Iran, a bit of Syria, Turkey, Greece, southern Italy, and then North Africa, Morocco, Algeria, these places. This is a graphic representation of the world's largest earthquakes ever recorded, these circles. The largest one, this bluish circle here, was in Chile in 1960, 9.5 Richter magnitude. And the purple circle here is the one we'll be talking about, is the sixth largest ever recorded of Chile. The mechanism of earthquake generation, in this particular case where the Nazca is pushing the South American plate, is by subduction. The plate goes under the South American plate and generates an earthquake when it snaps. The chimneys we're talking about are two chimneys, 128 meters high on the left and 100 meters on the right, at the Bocamina 2 power plant here on the right, and at the Colbún power plant on the left. These photos were taken after the earthquake, by the way. This is a schematic section through the height of the two chimneys. Again, these are, as you realize, new chimney design chimneys. Therefore, there is no liner, or in other words, the liner in form of pen guard blocks is glued at the inside of the concrete windshield. In these plants, the owner was Colbún for the Colbún plant and Endesa for the Bocamina plant. For both plants, the EPC contractor was Maire Engineering. The chimney constructor was Carena. Today, Carena is a part of the Dominion Group. The chimney designer for both the chimneys was AMTE. The chimney type, of course, was the new chimney design. The design took place in the period 2008-2009, and the construction was shortly afterwards, 2009 to 2010. The applicable design codes were the codes in effect in Chile at the time, which is the two earthquake codes. Interestingly, Chile has two earthquake codes, one for general buildings, this one here, and one for industrial structures. And this is remarkable because indeed industrial structures have different requirements and different responses than usual buildings. The American Code for concrete chimneys was also there, as well as the American Concrete Code, and of course all the other American codes like the Loading Code and so on. Additionally, the projects had specific, more stringent seismic design criteria set by the consultant of the owner, Professor Ernesto Cruz, and of course the soil report. Since there are several gentlemen from India, in this graph of the design response spectra, I have introduced the Indian response spectra for the three highest zones, 5, 4, and 3. And in dashed line are the design spectra for the two projects that we're talking about, Colbún in blue and Bocamina in purple. You can see that the requirements of this project were similar, more or less, to what one would have expected between Zone 5 and Zone 4 of the Indian Code. As we started the design, obviously we did some research, and here on the left you see a listing of the earthquakes above 7.5 Richter that had been recorded in Chile, and you see it's quite a few, not to mention smaller than 7.5. So basically this tells you that at this frequency, the occurrence of a major earthquake within the life of the chimneys was essentially guaranteed. Usually it's probabilistic, usually it's bad luck. With this history, you were assured to get a big one. Of course, we didn't know it would happen a few months after construction. Looking at failures of concrete chimneys, there aren't that many reported. The most famous one is probably the failure of the Tupras refinery chimney in Turkey following the Kocaeli 1999 earthquake. It was a 115-meter high chimney, and it failed due to a failure of the opening region. Thermal cracking is usually what is associated with failure in chimneys. This is an example here of typical thermal cracking and inadequate horizontal reinforcement. There is, of course, a case where a chimney collapsed in India in 2009 during construction, during slip forming, at 240 meters out of the, I believe it was 270. This was probably apparently attributed to concrete strength issues during slip forming. So the general methodology followed for the seismic design was as follows. Chimneys, of course, were designed on the basis of forces determined from a response spectrum analysis using the design spectra of the project. Now, because of the seismic environment, the chimneys were detailed for ductile behavior, and we used the CISIN code recommendations for that, which involve limitation of the horizontal bar spacing, increased lap splices for the vertical bars, and limits set for the reinforcement ratio with respect to the axial forces, vertical reinforcement ratio. Now, going to more specific issues, we used reduced behavior factors at critical locations to ensure satisfactory post-earthquake response, which means resistance to aftershocks. The American Chimney Code at the time, and so did also the design specifications, project specifications, specified a behavior factor R1 equals to 3. This was not a good choice, but it was common at the time. We used in this project 1.5. And this is the value that now the current American code has changed into. The chimney, being a cantilever structure, does not have any reliable mechanism for developing plastic hinges without essentially collapsing. That's why one has to be very careful about the assumptions one makes about structural damage and without failure, without collapse. Additionally to this reduced factor, the bottom part of the chimney was designed elastically, because it's not shown here, there's also another opening, large door opening. So we decided that we needed to design that elastically to protect the chimney. Another special issue in chimneys that are tapered, if you remember Professor Gleick's lecture 2 weeks ago, he had mentioned that up to a certain height, new chimney design, chimneys may be cylindrical. In our case, we deviated from that because we have a much higher requirement from the earthquake than usually happens with wind. That's why both chimneys are tapering up to a certain height, approximately up to mid-height. Tapering chimneys have particularities where the second and third mode become more important in a vibration than usually for cylindrical chimneys. Therefore, we assumed an increased participation of the second and third mode. This is an example. In a cylindrical chimney, you would expect 60 to 70% participation of the first mode, while in a tapering chimney, this changes drastically. And similarly, second and third mode participation are increased in the tapering chimney. This is important because it gives us significant moments at these locations. And of course, since the behavior of a chimney in an earthquake is not idealized, it's not a sum of modes, but it's a forced vibration, these increased moments could manifest anywhere along that height. We used 2 sets of models for the design. We usually do that in important projects. One is the design set, and the other is the verification set, to make sure that we control the results entirely. Each one consists of a beam element model without the foundation and of a finite element model detailed with all openings and foundation. And you can see here the comparison of the results in terms of vibration characteristics with different models. This is the finite element model, and you see, for example, here on the second mode, you see the high stressing of the region of the opening. The chimneys, I forgot to mention, have 2 inlet openings. One is here and one is there. So This is already highly stressed on the second mode. And on the third mode, you see here also a rocking mode of the foundation. In the Colbún foundation was a flat slab, and the Bocamina foundation was on piles. So this image is for the Colbún chimney. Very importantly, very importantly, proper detailing of the reinforcement around the openings, of the additional reinforcement around the openings, which has been calculated in detail by finite elements and also had to respect the requirements of the code. You see here the sketches in the calculations to ensure that the reinforcement was placed correctly around the openings. Now the ductility checks were carried out. This is a snapshot from the design calculations. We needed to maintain a limit on the vertical reinforcement ratio, limit which is dependent on the axial force on the chimney. That's why it's different along the height. And this is the ratio provided, always lower than that limit, in order to provide the chimney with ductility. We're going now to the earthquake. On the 27th of February 2010, a large earthquake struck Chile, on the map here on the left. This is the southern part of Chile, and the blue dot is where the chimneys were. So the epicenter was very close to the chimneys. You can see here on this map better. This is the epicenter here. This is the southern part of Chile. This is part of this map. In the town of Coronel, this is the town of Coronel from Google Earth, and this is where the two chimneys were located. This is the Colbún plant, and this is the Bocamina plant. These pictures are after the earthquake from the city of Concepcion, which Concepcion is this city here. The earthquake had the magnitude of 8.8 on the Richter scale. It is today the 6th largest earthquake ever recorded. 450 deaths occurred during that shock, and more than $30 billion direct financial losses, I mean direct damage. And you see here some examples of this damage. You see a failed, you can tell that the floors have collapsed, a failed multi-story building here, over here a different one, and here, this is a before and after photograph, an apartment building that completely collapsed. You see failures at the shear walls at the base of this apartment building, a bridge that lost its support, and extensive damage to industrial facilities where we have heavy loads such as these silos which toppled and buckled. I don't know if you're familiar with accelerograms, but I can assure you that you are looking at a monster here. Just from the duration of the large motion, which is anything above 0.20 G, you have almost a minute and a half of over 0.20 G shaking. And then you have peaks that reach up to 0.59 G. This is a very large earthquake. Of course, because it's large in magnitude, it's also large in duration. A lot of energy in a long period of time. So structures that don't have reserves cannot make it. Very importantly, because this was an epicentral earthquake, you also had a significant vertical component, 0.57 vertical component. This is very important because usually codes do not prescribe simultaneous combination of vertical and horizontal components for earthquake. In this case, this creates a problem because you realize that the vertical earthquake stresses the vertical bars and therefore reduces their capacity in bending. At the power plants, there was damage. This is an excerpt from newspapers at the time, where both utilities asked for extension because of damage sustained from the earthquake. And interestingly, there was a low chimney at the Bocamina plant, the existing Bocamina 1 plant, 30-meter high concrete chimney, which was severely damaged. And you see here some damages from the earthquake. At the bottom is a control room, a ground level building where all the non-structural elements were completely destroyed. And here, a portion of a duct can that was not yet bolted shifted. Now, this is the response of the chimney to the accelerogram. This is a time history of the displacement of the chimney following the accelerogram. You will see to the right, as we go up and down the history, the chimney, the behavior of the chimney, and you can notice the combination of the vibration modes. The first being the simple cantilever, the second, the third, sometimes the fourth. And you see that the combinations change. And that is why you don't really know exactly where that maximum moment would occur when you're designing. But by looking at this, you can tell that you need to take into account all kinds of possibilities. Now we're at the peak deflection. And then we are now at 30 seconds, and we're still going up to 100 millimeter deflections. Now we have reached 38 seconds, and still the shaking is very significant. This would have been a major earthquake, even this part of the accelerogram, in any other part of the world. And then slowly the chimney dampens out. There is a small increase here of acceleration, but it will dampen out eventually. After the earthquake, both chimneys were inspected by a team consisting of Professor John Wilson from Swinburne University of Technology in Melbourne and by Mr. Marcus Rost from Constructure, whom you had the pleasure of hearing last week. You see the photograph here of the chimney. Keep in mind that we were a few months after construction of the chimney, so the inlet duct had not been yet put in place. The chimney was completed, concrete and Vanguard blocks, as you see here, was finished, but only the guide vanes were in place. So the inspection yielded that there was no damage in either the concrete or the lining, that is the Vanguard blocks. Now let's look at the response. What I've plotted here is the moment, the bending moment along the height of the chimney. The yellow line is, as I mentioned before, the Indian code and the response from the Indian code. The green line is the response from the project specifications. You can tell here that there is a slight increase, but otherwise they are quite similar. The red and the blue lines are time history curves from accelerograms. The blue one is the actual earthquake from Chile, the accelerogram from Chile, and the red one is a famous earthquake from the literature that usually we compare big earthquakes to, the Loma Prieta in California in 1989. So you can tell the huge difference between the actual demand and what had been the design requirement. Now, these were the approaches during the design, that is that the bottom part be designed elastically so we were able to cover this distance, while this part had an increased factor, not as large as the bottom, which corresponded to the increased participation of second and third mode. Now, this is an example of a time history of a moment, looking at mid-height chimney about here. This is the bending moment along the time of the earthquake. The dark lines are the design requirement, the design moment. And the red lines is the capacity that was given through the provision for increased second and third mode participation. And there were only a few peaks which are covered essentially by the safety factors that are above this line. So basically this allowed us to have a chimney withstand this earthquake without damage. Now, what would happen had it not been a new chimney design? New chimney design is on the left, and a traditional chimney is shown on the right. By traditional, I mean not brickliner, because that would have been prohibitive in a high seismic environment. It is a steel liner with Vanguard inside. I kept that solution so that the Vanguard cost would be the same in both cases. We have a much larger concrete structure, obviously, in order to be able to include the lining. This is an approximate estimate that the seismic mass of this chimney is about 50 to 60% larger than this one. Let's see the response now. The response of the quote-unquote regular chimney is in the dashed lines here. So the comparison between new chimney design and regular design would be the comparison between solid lines and dashed lines. And you can see the very large difference, for example, in the Chilean earthquake response between here and here for this heavier and stiffer chimney. So this is the problem. The chimney is heavier in mass and stiffer, and that is why it absorbs more earthquake energy. And that, of course, can be seen here. The big difference that you see is not just the difference in the base moment, but also along the height, a very large difference. I've put here the differences in moment at the base and at mid-height approximately. So you can see that we're above 100%, double the requirement in moment at mid-height, and about 100%, 80 to 90% at the base. This would require a much larger structure actually. And if we put it down in terms of numbers, as mentioned, the windshield is about 60% more larger in terms of concrete quantities, the liner is the liner, so you have to add a liner and its corresponding platforms and supports. The foundation is increased by about 50%. This is an interesting fact because usually in the new Chimney design, we have a foundation that looks proportionally larger compared to the very slender windshield, but in fact it is not if you compare them in actual quantities. In the seismic case, you have a foundation of the regular chimney that is a lot larger, it doesn't just look larger, it is a lot larger because it needs to prevent overturning. And the additional weight of the structure is not enough to provide the resistance to overturning. That's why also the foundation is a higher cost. It's a larger foundation in diameter and in thickness. So in concluding, the obvious conclusion actually is that in significant seismicity regions, special care is required for the design of tall structures, not just chimneys. The new chimney design results in a much more slender structure, which improves the seismic response. It's very similar to what you see in trees. A very stiff tree in a windstorm will topple, while a flexible tree will be able to take the wind. The new chimney design results in significantly lower quantities, as you saw before, compared to the traditional steel liner approach. Again, brick liners should not be used in a seismic environment.